Okay, so hopefully that was fun. Drawing two particular triangles out of infinite triangles you could have drawn. Okay, maybe we can leave this up. I'm sorry? It's basically using Snell's law to do ray tracing to figure out the displacements of rays that comes out of a single source, right? Okay. Alright, so let's continue on our little ray chapter, the last chapter we'll be covering before the final. Objects, apertures, hopefully, you know, how to deal with magnification, blind spots. Okay, we did reflection, and I think we finished up refraction, right, last time. Keep going down, right? So this example was this one that's basically very similar to the, okay, you guys were not looking at anything. This example, right, is basically the similar to what we just did on the worksheet, where a light source comes in and it gets displaced because it went through a material that has a different index of refraction. Okay, so keep going down. Total internal refraction. We talked about that, right? And then we talked about fiber optic. I think this is where we ended up yesterday. Okay. Just so you know. So what we're going to do now is going to talk about image formation by refraction. Okay. And basically this is going to take us into the last thing we're going to cover, which is on how lenses work. How do you figure out what the focus and where the image will be formed? Okay. So let's think about let's say we have our little eyeball, right? And then we have a flying fish in the air. Okay. So typically what happens is that you have an object, right? Remember, when you have a single object, you should think about these as just producing rays that comes out in every direction, right? Okay. Okay. Some of these rays will be captured by your eyeball, okay? And your eyeball, right in front of your eyeball, is the lens. This is the lens of your eye, right? And then that lens will focus all of those rays that actually hits the lens into a single point in the back of your eye, and this is how you're actually able to see the fish, right? Okay, so let's see what happens if, right, instead of the fish being in the air, which is unusual for a fish, right, let's say the fish is in water, right? Okay, ignore this orange fish for now. Okay, so this object, right, still produces rays that comes out, right? Okay, and what happened is that the light will refract. I know this is hard to see, right? There's actually a bend in the light here, okay? I wish the book actually made it more obvious. The light comes out, and there's actually a slight bend in the light, okay? It's not going in the same direction, okay? If it was going in the same direction, it will continue on like this way, okay? Okay? So there's actually a slight bend in this light. And what happened is that, well, then it makes it so that it actually goes out at a bigger angle, right? Hits your eye and then comes back in like this, okay? What we need to do is that, well, from your eyeball's point of view, the top of your lens and bottom of your lens, actually, instead of tracing back to the original object, it actually traces back to a different spot, okay? This is known as back tracing. This is where these little dotted lines come from. So if you follow the straight line this way, it actually goes in. When it gets into the water, instead of following the solid purple line, it follows the dotted line. That's the straight line. And so the image actually appears closer to you through a fish tank. Okay, and this is going to happen if I think usually like a Chinese restaurant has these fish in their tanks, or if you go to the market or something like that. Right. This also happens if you are trying to get something out of the pool, and you're just trying to get it, and you know approximately what the distance is, but then you grab it, it doesn't. You actually don't get the thing, and that's because objects that are in water appears closer to you than they do if they were in the air. So how do we deal with this? Okay. So what we're going to do is we're going to draw a blown up version of the fish example where we have an object right? Let's say instead of having a small angle diffraction, we kind of exaggerate the diffraction so that it actually kind of goes this way, right? Same thing on the other line that's going to the going to the bottom of your lens, okay? What happened is that, right, in the transition from the index of refraction N1, which is the water, right, into index of refraction N2, which is air, okay, right, you're going to have this bend in the rays, and then when you backtrace along a dotted line, the image will actually appear closer to the surface than it would otherwise, okay? You can go through some geometry, right, where this is the length L, right, so we're drawing triangles once again, right? I'm going to highlight this triangle, right, this triangle, right, okay, okay, and this distance here inside here, ooh, right, this distance inside here, right, basically the actual depth of the object, how deep is it in the water, I'm going to call that S, okay, right, because S sounds like fish, okay, right, where the object actually appears to you, okay, I'm going to draw that with my green triangle, okay, green triangle, right, they're offset from each other just so you can see both triangles, right, okay, the leg, well, the length of this triangle, I'm going to call that S prime, okay, the prime stands for the image, okay, is how it appears, the one without the prime is the actual value in real life, okay, right, so just doing some trigonometry, okay, what will happen is that since both these triangles have the same length L, right, on this leg, right, the green triangle and the yellow triangle has the same length L, what you can derive just using a little trigonometry is that, S prime is going to be equal to S, but multiplied by this factor of tangent theta 1 over tangent theta 2, okay, with a negative sign in front, okay, because it's actually the difference between them that you're going to see, okay. All right, so tangent functions is, going to be interesting and funky, right? So what we're going to do is going to start doing some approximation where, let's say, right, for small angle, the tangent function and the sine function are approximately equal to each other, okay? These are going to be similar to each other. So therefore, this ratio here, okay, we can approximate that as, well, sine of theta 1 divided by sine of theta 2, and we know exactly what that is because Snell's law tells us that this ratio is going to be, right, n2 over n1, okay, right? So equating this, what will happen is that this is exactly equal to basically negative s over s, s prime over s, okay? So combining that, you can actually derive that the image, right, how deep the fish appears, right, is going to be equal to how deep the fish actually is multiplied by the ratio of the index of refraction, okay? Okay. So since the index of refraction of 2, which is air, is 1, index of refraction of water is 1.33, so it's going to appear basically 1 over 1.33 closer, or about 0.7 closer to the surface than it would. This negative sign is going to be interesting, okay? We're going to need to keep track of it, right? This negative sign just came from the derivation from the geometry here, right? What that negative sign means is that we needed to do some back tracing to figure out where the image actually gets formed, okay? If the image actually forms outside here, that would be a positive value, okay? The negative sign comes from the fact that it actually forms inside the water still, okay? We're going to see that the next section, this is actually going to be considered a lens, and we're going to see how that's going to play out, okay? So for now, just kind of say that negative sign and just kind of ignore it for now. It's going to be important in the future, okay? Whether or not the image will form in front of the lens, sorry, after the lens or before the lens, okay? All right, so let's do a little quick example, okay? So let's say you are in a ship and there's a fish and a sailor looking at each other. You know how fish loves a sailor or sailor loves fish. I don't know which way the affection goes, okay? And they're looking at each other through a 5 centimeter thick glass porthole in a submarine. And there happens to be an air bubble right at the center of the glass, okay? How far behind the surface of the glass does the air bubble appear to the fish, and how far does it appear to the sailor? Okay, so what I'm going to do, I'm going to do a drawing for the fish. So the fish is going to be in water, hopefully, right? So you are a fish. This is the best fish I can draw, okay? and the fish is looking at the submarine, and there's a piece of glass in there. I'm just going to draw that glass square, okay? And there's an air bubble right in the middle of that piece of glass, okay? Right? So that means the thickness of the glass is 5 centimeters, right? That means the air bubble is actually located 2.5 centimeters inside the glass, okay? Okay. The index of refraction of glass, we're going to use 1.5. Index of refraction of water is 1.33, okay? So what happened is that you're going from an area of high index of refraction to low index of refraction, so the bubble is going to appear closer to the surface, to the fish, okay? All right. So what we're going to do is we're going to apply the equation we just derived. So where the image appears to be, right, S prime, right? Okay, I'm going to draw that in purple, right? This distance S prime, right? Oops, not S1, S prime, right? And then the distance to the real bubble, okay, what should that be called? Anyone want to guess? Just S, right? The prime is the image value, right? The one without the prime is the real value, okay? Right? That's going to equal to the ratio of the index of refraction. So the light is coming, right? The source of the light is actually coming from the glass, right? That should be called N1, right? N1 equals to 1.5, and then N2 is where it exits and goes into a different medium. That's 1.33, okay? So N2 over N1 times S, right? And if you plug in those numbers over here, right, I kind of copied it so I save some time in doing the calculator punching, okay? So the image is actually going to appear 2.2 centimeters from the surface instead, okay? And this is known as a virtual image because it's actually not out here, right? The bubble doesn't appear up here. That's why that negative sign is there. We're going to see how that's going to play out when we do lenses, okay? Does that make sense? All right. So maybe now you guys can figure out how to deal with it with the sailor. Okay, so we have a sailor. I don't know what sailor actually wears, like maybe a hat or something like that. And then she's looking the same piece of glass with a bubble inside. Okay. The only difference in this case, right, is that instead of going from glass to water, we're going from glass to air, right? Because sailors don't breathe water most of the time. Okay. So the only thing we need to change in the equation is actually this value up here, right? That's the value of the index of refraction of water. Okay, if we did that, okay, what will end up happening, the image will actually form, right, closer to the surface of the glass, or 1.7 centimeters from it instead. Okay, so that little bubble appears closer to the surface to the sailor than it does for the fish, right? Because the change of index of refraction between glass to air is bigger than the index of refraction change between glass to water, right? All right, any questions about this? You doing okay? All right. Okay. A lot of these problems, just as you guys did on the worksheet just now, right? It's actually figuring out what what theta 1 is, what n1 is, and n2 is, right? Those are the hard part, okay? Because that's going to change, whether or not, because if you flip this, right, you're going to get the wrong answer, right? Okay. All right. Got a lot of space here for some reason. Okay, so before we move on to thin lenses, which is what we'll end up in 4 minutes here, right? I just want to make sure it gives you guys another definition. So this ratio, right? So if we start off with this equation here, negative n2 over n1 equal to s, right? You can actually kind of massage this equation, basically divide both sides by s. This will go away. You can derive this equation where it's basically the ratio of s prime over s, and that's actually going to be the ratio of the index of refraction with a negative sign in front. Okay? This s over s prime with the negative sign, if you bring this over, right? This is actually known as the lateral magnification. Okay? Don't worry about the lateral yet. Just think of it as magnification, because the object actually appears closer to you, right? Right? So it's actually magnifying that object for you. Okay? Which is kind of neat. Okay, so I'm going to start talking about a little bit about lenses. We're not going to be able to finish it in 3 minutes, but let's just get started here, and then we can, on Monday, we'll do a worksheet on this also. Okay, so thin lenses, okay, it's basically a way for us to manipulate light, either by accident or by design, such as your glasses. Okay, so that you can actually change the direction of light so that it actually, you know, either converge at a different spot or not converge at a particular spot, so you don't want to burn something. Okay, so a lens is actually made of 2 spherical surfaces. Okay, the reason they are made of spheres is because spheres are actually easy to make out of glass, and then what they do is they just glue them together. Okay, um, okay, so there are 2 different types of lenses. There's converging lenses, and hopefully it sounds like what they will do, right? If you have parallel rays, it doesn't matter what the color is. I don't know why the book decided to use colors here, right? You have parallel rays coming in here. On a converging lens, it will converge into one point after behind the lens. The real image will be converging, okay? For a diverging lens, which is basically made of 2 pieces of inverted spheres glued together, okay? Instead of converging, the rays will actually diverge away from each other, okay? And what we need to do is actually backtrace this back to here, but we're going to play with, deal with diverging lens after converging lens, okay? Okay. So, what was I going to talk about here? Yeah, so each of these lenses are actually made of half a sphere. So if you imagine, if I have one circle like this, right, one sphere made of glass, I cannot draw circles at all. This is horrible, right? And then you draw another circle that could have a different radius. Let's say I draw another circle that has a radius like this, right? And then you basically cut this like this, right? You'll basically make a lens, okay? So I'm going to draw the lens part in red here, right? That's basically how you would make a lens, okay? And the radius of these circles is going to give you different, what we're going to learn about is going to be what's known as the focal length of the lens, okay? The focal length of the lens is where the rays will converge into a single point for a converging lens, okay? So all the parallel rays comes in here, they're going to converge in this one single point, and it's going to converge at a distance f, called the focal length, behind the lens, okay? Diverging lens is a little bit more complicated because they don't actually converge in a single point, right? You can follow these rays out to infinity and they will never come together. So in diverging lens situation, what you need to do is do this thing called backtracing, where instead of going forward along the ray, you do these dotted lines and they all come back to the same point, okay? This is the focal length for a diverging lens, okay? Okay. So when the last rule before we wrap up today is that when a ray hits the center of the lens, they don't get bent, okay? So you can do some geometry to figure this out, but, right, when it hits the surface, hits the exact center of the lens, the rays doesn't bend. You know, the easy example is this one, which is this horizontal, right? It doesn't get bent. But even if it comes in an angle like this, actually the rays does get diffracted, but then actually it goes like this and then goes out, so the rays doesn't get bent. In the approximation that these lenses are thin. So the thing we did in the example, right, if you have a thick lens, they would get displaced, but they would come out at the same angle still, okay? All right, so I'm gonna wrap up here today, and I'm going to do some how we deal with converging lenses and diverging lenses on Monday, and hopefully we'll have time to do